Welcome to the video tutorial series presented by Elisa and Walchand College of Engineering, Sangli. I am Eliside Sachin. In this tutorial, we are going to study about the different biasing methods of BGT. So, the agenda of our discussion will be the need of biasing. And in this, we are going to study about what is biasing, stability factor, and thermal runaway, and also the methods of biasing. That is fixed bias, emitter bias, collector to base bias, and voltage divider bias. So let's move on. What is the need of biasing and why it is required? So the basic function of a transistor is to do amplification. That is, the weak signal is applied to the base of the transistor and amplified output is obtained at collector terminal. That is, then what is faithful amplification? The term is that the increase in the magnitude of an small input signal without changing its shape. That is the faithful amplification. Or in the second way, the biasing refers to the application of DC voltages to set up the operating point in such a way that output signal is undistorted throughout the whole operation. Underline the word whole operation because it is very important. And the second need is the making operating point independent of temperature. And last is the to avoid the thermal runaway because due to the thermal runaway, transistor may burn out. So this is the need of biasing. So what is biasing? What is biasing? Biasing is the selection of Q point such that it should not differ the changes in the IC. That is, changes in IC is due to the beta variation of replacement of transistor of same batch or different batch. And second is temperature variation due to the changes in IC. So the main purpose of the biasing is to keep the base emitter junction forward biased and collector to base junction reverse biased. That is the main purpose. So for biasing, we need the stabilization of operating point. Then question arises that what is stabilization? Stabilization is the process of making operating point independent of temperature changes or variations in transistor parameters is known as stabilization. So for stabilization, so we need to study about stability factor. Stability factor. Stability factor means the rate of change of collector current IC with respect to the collector leakage current ICO at constant beta and IB. It is called as stability factor. So what is ICO? ICO is the reverse leakage current flowing through the collector to base junction of a transistor when emitter terminal is open. That is, we define S as the, by definition, stability factor is the rate of change of collector current with respect to leakage current at constant beta and IB. That is, it means that the rate at which IC is changing whenever changes in ICO. That is, it means that if S is small, then changes in corresponding IC will be smaller. That is, circuit has good stability if S is small, and vice versa. If S is high, the circuit has very poor stabilization. By seeing from the equation, the IC equal to beta IB plus beta plus 1 ICBO. That is, beta IB is the majority current and beta plus 1 ICBO is the minority current due to the reverse leakage charges. And the differentiating above equation with respect to IC, we get the 1 equal to beta into DIB by DIC plus beta plus 1 into DICBO by DIC, and by solving we get S equal to beta plus 1 upon 1 minus D1 minus beta into DIB by DIC. That is the about stability factor. So we need to consider relation between stability factor and thermal runaway. By seeing again this equation, we seen that the collector leakage current ICBO is strongly dependent on temperature. The flow of collector current produces heat within the transistor that raises the transistor, and if no stabilization is done, the collector leakage current ICBO also increases. It is clear from above equation that If ICBO will increase, the collector current IC will increase by 1 plus beta times ICBO. Instead of IC will rise, the temperature of the transistor also rise, which will in turn will cause ICBO to increase. This effect is cumulative, and in a matter of seconds, the collector current may become very large and the transistor may burn out. So that as the actual thermal runaway means the self-destruction of an unstabilized transistor is known as thermal runaway. So let's move on the different methods of biasing. It is here in this methods of biasing of BJT. In following each method, we are going to find out the operating point of that bias circuit and also find the stability factor for deciding circuit is stable or not. So let's move on the first method, that is fixed bias. Fixed bias. In fixed bias, we have used the single power source used for both collector and base of a transistor. So by applying Kirchhoff's voltage law to the input loop, we get VCC minus IBRB minus VB equal to 0. That is IB equal to VCC minus VB by RB. From that, IC equal to beta times IB we can easily find out. Then apply the Kirchhoff's voltage law at output loop. Then we get VCC minus ICRC minus VCE equal to 0. That is VCE equal to VCC minus ICRE. Then we get both IC and VCE, that is the operating point. So from above equation we see that if we differentiate equation 1 with respect to IC, we get dIB by dIC equal to 0. Then we get S equal to beta plus 1, that is very high. So the advantages of fixed bias method are biasing conditions can easily be set by calculation are simple, and there is no loading of the source by the biasing circuitry. And the disadvantages of fixed bias method are this method provides very poor stabilization because of the very high value of stability factor, that is beta plus 1. It means that very small changes in ICBO makes very large changes in IC. So that is not good for the biasing circuitry. Transistor may burn out. So next method is emitter bias. Emitter bias method is introduced because to improve the stability of the circuitry. In this method, simply an emitter resistor is connected at the emitter terminal of the transistor to improve the stability of the circuit. For the analysis of this circuit, first step is to apply the Kirchhoff's voltage law to the input loop, that is VCC minus IBRB minus VBE minus IERE equal to 0. That is by solving we get IB equal to VCC minus VBE divided by RB plus 1 plus beta times RE. That is the IB, and apply the Kirchhoff's voltage law at the output loop. Then we get VCC minus ICRC minus VCE minus IERE equal to 0. That is VCE equal to VCC minus ICRC minus IERE equal minus IERE. So that is we get IC and VCE, that is the value of operating points. By using the first equation, we can find out the stability factor, that is equal to 1 plus beta upon 1 plus beta into 1 plus beta into 1 divided by 1 plus RB by RE. That is, if we make RB is very less than RE, then stability factor goes towards the 1. That is, we have the very good stability of the circuitry. Then for improved stability of the circuit, we have to make RB which is less than RE. So what is the advantages of this method? The addition of the emitter resistor is to the DC bias of the BCC provides improved stability, and if we design this circuit very properly, then we can get a proper stable Q point also. The next method is the collector to base bias method. This method is one end of the RB is connected to the base and another end of the collector, as shown in the figure. Here the required base current is determined by the not VCC but by the collector base voltage. It is clear that collector to base voltage Forward bias is the base emitter junction and hence base current IB flows through RB. Also, this configuration employs the negative feedback to prevent the thermal runaway and stabilize the operating point. So we analyze this circuit, that is apply the Kirchhoff voltage law at input. We get VCC minus RC into IC plus IB minus IBRB minus VB equal to 0. By arranging this equation, we get IB equal to VCC minus VB divided by RB plus 1 plus beta times RC, and then apply the Kirchhoff's voltage law at the output side. We get VCC minus RC into IB plus IC minus VCE equal to 0. That is, we can find out VCE equal to VCC minus RC into IB plus IC. So by using the first equation, we can find out the value of S, that is stability factor. S equal to 1 plus beta divided by 1 plus into 1 plus beta into 1 divided by 1 plus RB by RC. From equation, it is seen that if we make RB value very less than RC, the value of stability factor goes to the 1. For making circuits to be good stable, we have to design the value of RB such that it is less than RC. So what is the advantage of this method? The stability factor somewhat improved, that is stability factor is less than beta plus 1, that is it is greater thermal stability than the fixed bias. And disadvantage of this circuit is this circuit uses the negative feedback which reduces the gain of the amplifier. So the last method we have to study here, the voltage divider bias. Voltage divider bias, it uses the divide circuitry, that is R1 and R2. Voltage divider bias is the most popular and used way to the bias of transistor. It uses few resistors to make sure that voltage is divided and distributed into the transistor of at correct levels. One resistor Re helps to provide stability against variation in beta that may exist from the transistor to transistor. So by seeing from the figure, we have to convert this circuit to the Thevenin equivalent circuit. In that, we find that VTH equal to VCC into R2 divided by R2 plus R1 by the voltage divider rule, and RTH equal to the R1 parallel R2, it is R1 R2 divided by R1 plus R2. So apply the KVL at input side, we get VTH minus IB RTH minus VB minus IR equal to 0. By arranging this equation, we get IB equal to VCC minus VB divided by RB plus 1 plus beta times RE. And same, if we apply the Kirchhoff's voltage law at the output side, we get VCC minus ICRC minus VCE minus IARE equal to 0. Then we find out the VCE equal to VCC minus ICRC minus IARE. So from that we get both values of IC and VCE, that is the Q point values. Then for the value of stability factor, use the first equation, and we have found that S equal to 1 plus beta divided by 1 plus beta into 1 divided by 1 plus RTH by RE. It is seen that if we make RTH very less than RE, then the value of stability factor goes towards the 1. So by making value of RTH very less than RE, we can obtain the improved stability. So in this circuitry, see here how emitter bias resistor Re fights against instability of beta. That is, the Re provides stability in gain of emitter current of a transistor circuit. Its gain amplification factor can vary by large amounts from transistor to transistor, even if they are the same exact type from the same batch. There is no replication of same exact beta across the transistor. Therefore, then we have to design transistor circuit where we want roughly the sum gain. For that, we need the Re resistor. So advantages of this voltage divider bias method is stability factor, yes, obtained is ideally 1, but practically it can be achieved up to 10 by arranging the proper values of R2, R1 and RB, RE. So it is good for us to value has the stability factor value has very less. So, and the second advantage of this method is greater thermal stability by avoiding the thermal runaway. And the last advantage is this method is very popular and widely used in the most of the amplifier circuitry. So the thank you and hope you have understood all the things. Thank you. For any suggestion, mail us at walchan.elisa@gmail.com and like us on www.facebook.com/wcelisa.